Today we'll look at the last 2 pages of the note pack for chapter Unit 5 for the factoring portion. The fundamental theorem of algebra states that for any polynomial of degree at least n of 1 that has complex coefficients, allowing you to have coefficients that have i's, but you don't necessarily have to have i's. So if your degree of your polynomial is 1, so it's at least linear, could be quadratic, cubic, quartic, etc., that you absolutely have to have at least one complex zero. Now remember, we can get caught on the word complex. Complex means there might be an I in the zero, but that's not necessarily. If I have a plus bi, the b can be equal to 0 and it just be a real 0. So this theorem, fundamental theorem of algebra, doesn't really sound that awe-inspiring. It just guarantees us that if we have a polynomial, regardless of the coefficients, that has degree 1 or higher, that you have to have at least one complex zero. More importantly, is another theorem that can be proven from that theorem, is that the number of zeros that your polynomial will have, if it has a degree at least 1, will be exactly equal to the degree of the polynomial itself, if we count the multiplicities. So if I have a polynomial that is of degree 7, I am guaranteed that there are 7 zeros. Some of them might have an I in terms of the coefficient, some may not. But I'm guaranteed that the number of zeros is equivalent to the degree, as long as I count the multiplicities. So up here, if we had a quadratic, we know a quadratic is going to have degree 2, so we're guaranteed to have 2 complex zeros. Now, the 2 complex zeros might actually graphically be 2 real zeros. That would denote when we graph it that it crosses the x-axis in 2 places on the x-axis. It may appear as though it only crosses it once, but we remember from our study earlier that if we have a double root, so for instance maybe this is x plus 2 quantity squared, if this 0 is at -2, that if I count the multiplicities, I will have 2 zeros for my quadratic. Now in this third example, we can see that the quadratic that I just arbitrarily made up and sketched doesn't have any real zeros, but because it's degree 2, it's guaranteed to have 2 complex zeros. Now these 2 complex zeros do have imaginary parts. We can see that because the graph doesn't cross this axis. Now we'd review earlier what the multiplicities mean, and remember anytime I have a graph, this is degree 2, and a degree 2 graph is automatically going to have 2 zeros if I count the multiplicities. This happens to be a double root. This graph, if I multiplied out the expressions or the factors, I know I would have a degree 3, which means I'm guaranteed to have 3 zeros, 3 complex zeros. All 3 of these zeros have to be real if I count the multiplicities, 1, 2, 3. If I multiply this function out, I will have a degree 4. So I'm guaranteed by my above theorem that I will have 4 complex zeros. Now all 4 of these zeros actually happen to be real numbers as well. I have a multiplicity of 3 here. Make sure you accentuate that cubic looking kink here, and then it looks locally linear at the 0 of 4. Now in Algebra 2, you also had the complex conjugate zeros theorem, or the conjugate zero theorem. And remember, if I have a polynomial and the coefficients on the polynomial are real numbers. Now these coefficients for this theorem can't have i's in terms of the a sub n's. They have to be real numbers. They could be square roots, pi, e, integers, fractions, but they can't have any I component. And so if I have any polynomial in which I have real coefficients, if you know that you have a 0 that has an imaginary part, which means it would be a 0 that would not be crossing the positive x-axis or the negative x-axis. And so if a plus bi is a 0 to your function, then this theorem guarantees that a minus bi must also be a 0 for your polynomial. Again, I can't emphasize enough that that's only going to work if these coefficients are all real numbers. If any of these a sub n's have an I component, then the zeros will not necessarily come as complex conjugate pairs. And we'll see that when we do some factoring on this next question, how the conjugate pairs come about. So on this next example, we have a degree 32 polynomial. If it's degree 32, that means there are 32 complex zeros. We can find all these zeros by doing a little bit of factoring. I factored out my common factor of x to the 30th, leaving me with a binomial that's a quadratic. This binomial has to be factored over the set of complex numbers because we aren't going to be able to factor down unless we use the I term. So we have a sum of squares factorization. A 0 for this factor is 0. It actually has a multiplicity of 30, or we could have written that factor of x out 30 times, which would be a bit repetitive. The 0 for this function, or this factor, is negative 1/2 I, and the 0 for this is 1/2 I. Notice that these two are complex conjugates. This is 0 minus 2i, this is 0 minus 1/2 I, and this is 0 plus 1/2 I. The coefficients on this polynomial were real, so I knew once I had one 0 that had an imaginary part that its complex conjugate was also going to be one of the zeros of this polynomial. Now we're going to flip over to the back side before we talk about number 2. On the back side, I gave you quite a bit of this information so you didn't have to copy it down. But I have a polynomial here, x to the 4th minus 2x to the 3rd plus 6x squared minus 2x plus 5. I see that I have real coefficients on all of the a sub n terms. The complex conjugate theorem applies to this. If I know I have one 0 that has an imaginary part, then its complex conjugate will also be a 0. I showed some work here on doing the simplification out to show that I is in fact a 0 of this polynomial. When I plugged it in, simplified out, I got 0 for my expression. So I is a 0. What does that mean? Its complex conjugate must also be a 0. Negative I must also be a 0. Furthermore, I showed that if I take 1 plus 2i and substitute that in place of x, the independent variable, I also find that that is a 0 for my polynomial as well. There's a lot of algebra involved in working through this. We can use our calculator actually to show this substitution, and I'll quick show you that. I'm going to take 1 plus 2i, and I'm going to store it as x. And now I'm going to type in my polynomial of x to the 4th minus 2x to the 3rd, etc. So x to the 4th minus 2x to the 3rd power plus 6x squared minus 2x plus 5. And 1 plus 2i is what I had stored as x. And I can see that these values didn't come out to be exactly 0. These are some rounding error on my calculator. But that is 3 times 10 to the negative 12th power plus 1 times negative the 12th power I. And rounding error is occurring on my calculator, but that's basically 0.11 zeros and then 3 plus 0.11 zeros and a 1 I. All right, so we do have a little bit of error shown here. Now, as I said earlier, the complex conjugate, because of having real coefficients, the complex conjugate of this 1 plus 2i is also going to be a 0. If I take 1 minus 2i, store that now as x, and now instead of me typing that polynomial all over again, I'm going to actually do a second entry a couple times, so I have that polynomial coming back up. Now the calculator is remembering 1 minus 2i as my last input for x. And when I hit enter again, now I'm getting somewhat similar answer to what I had before, but this is basically 0. It just has some rounding error from my calculator. So 1 plus 2i and 1 minus 2i are both zeros because of the complex conjugates theorem. So because I is a 0, negative I is its complex conjugate is also a 0. 1 plus 2i is a 0, as is its complex conjugate. I knew my polynomial was degree 4 and that there were 4 zeros that were possible for this, and I have all 4, which means I can factor this down. Make sure you always remember it's always x minus a 0. It is never x plus a 0. Always x minus a 0. We usually change these signs to an addition sign here, but it still was x minus that 0, as is true over here as well. Now the last part is looking at the factoring of difference of cubes and then a few just general factoring questions at the bottom. In Algebra 2, you did a little bit of factoring of difference of cubes and sum of cubes. And we'll just review the basic formation for that. If I have a cube plus a cube, then in this case I would have x plus y is actually going to be a factor of that x cubed plus y cubed term. I could longhand divide x plus y into this polynomial and find out what the quotient is, but there's a quick way to remember it. The quotient, when I divide x plus y into this cube plus a cube, is going to be the square of the first term and then the opposite of the product of these two terms, so minus xy, plus the square of the last term. If you multiply and distribute all this out, you'll end up getting a whole bunch of things will cancel out except for x to the third and y to the third. Likewise, if I have a cube minus a cube, one factor of that expression will end up being x minus y, or the cube root of the first term minus the cube root of the second term. Now the resulting quotient, or the other factor, will end up being the square of the first term and then the opposite of the product, so that would be plus xy, plus the square of the last term. Now, the quotient that will result from this will never be able to be factored over the set of real numbers. You would always need to have to use complex numbers if you were going to break this down further. I have one little example here of factoring difference of cubes. You don't necessarily have to rewrite it in a form where you have it as a cube minus a cube, but you do need to identify that as being a perfect cube. And so once again, I take the cube root of this goes here. The cube root of the 64y to the 12th power, which happens to be the 4y to the 4th power, I have the cube root of that there. And then that is a factor. It would divide into it evenly. And then the resulting quotient, or the other factor, will be the square of the first. The opposite of the product of these two terms will be the middle term of the quotient. And then the square of the last will be this final term in this trinomial. So this will always be a trinomial. This will not factor down, and my directions had only to factor over the set of rational numbers. And in order to break this down, I would have to be able to use complex numbers, so that's as far as I would have to go. Now, if I have a cubic function, some cubic functions are relatively easy to factor, some are pretty difficult. Always try, if you have, particularly if you're not able to use a calculator to identify any zeros, always look at the polynomial in standard form and see if it's possible that you group two of the terms together and the last two terms together and pull out common factors from each to see if you create another common factor. So that's the case for this. I'm using factoring by grouping. Grouping the first two together, factored out the common factor of x squared, and was left with x plus 4. The second two, or the last pair, I had a common factor of negative 9, factored that out. Now, if doing that factorization of splitting it up into two pairs if that creates another common factor, then this technique is going to be successful for you. Because now I can pull out the common factor of x plus 4 and be left with the x squared minus 9. Difference of squares will get me my final factorization. Now, this technique of factoring by grouping does not always work. Sometimes you're going to have to graph the polynomial, look for a possible real zero, and then divide that either longhand or synthetically to create what that extra quadratic would be. Quadratic formula can always be used to factor down a quadratic. So with a cubic, you want to find a real zero. There will always be one, as long as you had real coefficients, and then use quadratic formula, or possibly might be able to just factor it to find the other two. Now I have a couple other examples here of factoring by grouping. I'll just show them up here. You can look through the work on your own and see how the resulting factoring is. But remember, if I say factor a polynomial in its fifth degree, you will have 5 factors as long as you are counting the multiplicities. In this final factorization, here's 1, 2, 3, 4, 5.